Okay, one last section in this chapter, but this can be the hardest section for most chemistry students, dimensional analysis. Dimensional analysis is a systematic approach to problem solving that uses conversion factors to move or to convert from one unit to another. That's a pretty long definition. It'll make more sense as we go through a few examples. So a conversion factor is a ratio of equivalent values having different units. So a conversion factor is a ratio of equivalent values having different units. Here's some examples of conversion factors. 1 week is equal to, now I think we all know what the answer to this is, how many days? Well, it's equal to 7 days. Notice how it's a ratio of equivalent, which means equal values, having different units. So for time, 1 week is 7 days. They're equivalent, but they're different units. We're going from weeks to days. So all we did is convert there from weeks to days. That's an example of a conversion factor. Here's another one. 1 year is equal to how many days? Well, 1 year is 365 days. Again, same length of time. This one is in years, this one is in days. So that's a conversion factor. Let's do one more that we're pretty familiar with. 1 dozen is equal to 12 eggs. Both mean the same amount. A dozen is 12 eggs. And so equivalent values having different units. That's what a conversion factor does. And we use conversion factors to switch from one unit to another unit. Okay. Oh, there's one more. 1 foot is equal to how many inches? In 1 foot there are 12 inches. Okay. So using conversion factors, a conversion factor must cancel one unit out and introduce a new one. And so when we're doing these calculations, it's going to look something like this. This is just an example. But if we started with 32 people and each person had 2 bottles, see how people divided by people cancel out? And now we're left with bottles. But then we do another conversion factor and bottles cancels out with bottles on top and bottles on bottom. Just like this, any number divided by itself is equal to 1. So we can cancel those out. Units can cancel out too. If we have grams on top divided by grams on bottom, they cancel out. That's equal to 1 as well. And so we can cancel those out. And that's what we'll be doing in this section. And so let's get the hang of it here. Let's learn the steps to solving conversion factor problems. This is very important. I hope that if there's one thing in this section we remember is this systematic approach to solving these problems. Step 1, you always take the number that they give you and put it over 1. Always include the units. So whatever number they give you in the problem, we put that over 1 and include the units. Step 2 is to write a new conversion factor that will cancel out your original units with another one. So we want to cancel out the original units and introduce a new one. And we continue to do that until we're left with the units that the problem is asking us for. All right, let's do some practice problems. I think it will make more sense. Practice problem number 19. All right, it says convert 35 days to weeks. And here's how I always do these problems. And for me, it helped, and I think it will work for you. 35 days, I'm going to underline it. That's what they give us. It wants us to convert that to weeks, so I circle it. Step 1 was to put whatever number they give us in units and put it over 1. So I always write 35 days. That's what they gave us. We have to start there. There's nowhere else to start. Put it over 1. Okay? I always put parentheses around them just to start. And we want to convert to weeks. So we're going to introduce a new conversion factor. There's a conversion factor that we know that goes from days to weeks. But first of all, it's got to cancel out this existing unit. The only way that days is going to cancel out is if you put it on the bottom. So we're going to put days on the bottom. And we want to go to weeks. So let's put weeks up on top. Now here's why this is called a conversion factor. In 1 week, there are 7 days. Okay? And so what we've done here is just created a way of getting rid of days and changing that unit to weeks. Days is on top, days is on bottom, we can cancel it out. So we draw a line through that unit. We can't cancel out the numbers, they must stay, but we can cancel out the units. Okay, and then we're left with this unit weeks, which is what we wanted. It wanted the answer in. And so if you look at this, is a simple math problem. We just times everything on top. So 35, and we're going to times that by 1. And we're going to keep everything on the bottom. We're going to take 1 and times it by 7. So 1 times 7. 35 times 1 is 35. 1 times 7 is 7. And so there you have it. 35 divided by 7 is, of course, 5. And so 5. But here's where a lot of students will like to just circle 5 and say, that's our answer. Okay, you're going to get it wrong. The factor, the number, is 5. But we also need the units. We have to keep this unit here, 5 weeks. So when you put your answer on the paper, I want you to put the number and the units, the factor and the units, and circle that, so 5 weeks. So if we have 35 days, we know that is going to be equal to 5 weeks. And so that is a conversion unit problem. Hopefully that helps you to see that. Let's go through let's see, I've got a couple more here. Let's do practice problem number 20. And it says to convert 672 centimeters to inches. All right, get my red back here. So step 1, write down what they give us and put it over 1. They gave us 672 centimeters. And then we want to go to inches. So I'm going to circle that. So write down what they give us and put it over 1. That's always our first step. Put it over 1 and draw parentheses around it. Now we're going to have parentheses here on our other conversion factors, so I'm just going to write them. And I can already say that if centimeters is up here, in order to get it canceled out, we need it down here. Now we just need a conversion factor that takes centimeters to inches. And lucky for us, they gave it to us right here. 1 inch is equal to 2.54 centimeters. So 2.54 centimeters is equal to 1 inch. Okay. And now our units can cancel out. Centimeters is on top. Centimeters divided by centimeters is 1, so we can cancel that out. And we're left with this unit, the inch, and that's exactly what they wanted. So we can stop there. So now we times everything across the top. 672 times 1 is 672. And 1 times 2.54 is 2.54. And so we can figure out what that is. I'll grab my calculator. 672 divided by 2.54. And my calculator is giving me 264 point, let's say 6. I'm going to round it. Okay, now a lot of you attempted to circle that and be done, but that will be wrong. I'll mark it wrong. You got to include the units. That's the most important. 264.6 what? What are we talking about here? Okay, so it's 264.6. What we're talking about is we canceled out centimeters, so we're talking about inches. Okay, and so that is a conversion system problem. We followed all the steps, and hopefully that makes sense to you. Okay, practice problem number 21. So let's see, I've got just a few more. Convert 1,892 milliliters to quarts. 1 liter is equal to 1.06 quarts. All right, step 1. I always like to underline what they give us and circle what they're asking us to find. They gave us this. They're asking us for quarts, so I'm going to circle that. Now step 1, we always put what they give us, put it over 1. So 1,892 milliliters divided by 1 is step 1. Step 2, we're going to make a new conversion factor. We're going to try to cancel out the existing one that they started with. If milliliters is on top, we know that milliliters has to be on bottom to get them to cancel out. Now we just need a conversion factor here that has milliliters in and quarts. Okay, but if you look here, they gave us 1 liter is equal to 1.06 quarts. We have milliliters, so we need to convert that to liters. I'm going to draw the metric system boxes, and the mnemonic killer, hippos, die by drinking chunky milk. The base unit is the meter, the liter, and the gram. Okay, if we're going to convert milli, this is the millibox, to liters, liters would be the base unit, so we need to move the decimal 1, 2, 3 times to the left. And so there's an understood decimal place right here, 1, 2, 3 times to the left. And so that is 3 parts there. So, okay, let's see. I'm going to scratch this part of it. And since I've converted it to liters, that is 1.892 liters. And now we have 1.892 liters. I'm going to put that over 1. And we're going to use our new conversion factor here. 1 liter is equal to 1.06 quarts. Our liter will cancel out, and we times across the top 1.892 times 1.06, and I get this number 2.0, it rounds to a 1, and our units that we have to write down are quarts. So if you had 1,892 milliliters of something, it would be equal to 2.01 quarts. Easy, and we're able to convert from different units. All right, practice problem number 2. It says, write the conversion factors needed to determine the number of seconds in 1 year. Okay, this is an interesting one. So what are they giving us in this problem? They're giving us 1 year. We want to know the number of seconds. So I'm going to circle that. So step 1, take what they give us, 1 year, and put it over 1. Okay, why do we put it over 1? It just helps us line up our conversion factors as we move across here. If years is on top, we know that years has to be on bottom. Is there a conversion factor that we know that takes years into something smaller? We can't really go to seconds because we don't really know that conversion factor. But 1 year, let's change it to, let's go to days. 1 year is equal to 365 days. Okay, now our years cancel out, so I cancel those out. Now we're to days. But we can't stop there because it wanted us to go to seconds. So let's continue on. Let's make another conversion factor. Days is on top. We know that days has to be on bottom. Is there a conversion factor that we know that breaks days into something smaller? Let's say 1 day is equal to, what, 24 hours? Okay, our days cancel out, and now we're to hours. But we can't stop there because we need to go to seconds. So let's keep going. We can put as many as we need in here to keep going, and you know when to stop when you get to seconds. Hours is on top. Let's put hours on bottom. In 1 hour, I don't know how many seconds there are, but I know that there's 60 minutes. Okay, and now my hours cancel out, and I'm to minutes, but I still need to keep going because we need to get to seconds. So let's make one more. Minutes is on top right here, so we know that minutes has to go on bottom. In 1 minute, there are 60 seconds. Okay, and so our minutes cancel out, and look at here, we're left with seconds. So now we can stop because that matches what we wanted to, what the problem asked for. So let's just hit equals. And now this looks like a complicated problem, but we're just taking these numbers across the top and timesing them together. We're taking all the numbers on the bottom and timesing them together. And if you look here, the only number on the bottom is 1. And so the 1 times 1 is 1. And so now all we have to do is do 1 times 365 times 24 times 60 times 60, and we got it. And so Let me see what that is on my calculator. Enter it in right. So I'm going to get this huge number, 3153600. Okay, hopefully that's correct. If I put in the commas here, and our units, don't ever forget the units, is seconds. And so that's a lot of seconds, but we started at 1 year. So in 1 year, there are 31,536,000 seconds. So kind of cool. We can convert from one unit to another. That's all we're doing. And yeah, that's what we got, so we did it correctly. Okay, practice problem number 23. It says, how many hours will you have lived on your next birthday? So of course this problem is going to be different for everyone because I'm not the same age as you guys. I think most of you are on your next birthday. Maybe most of you are turning 16 or 17 or maybe 18. I'm going to do this problem as if I was turning 16. So say I was 15 right now, I'm going to turn 16. And so how many hours will you have lived on your next birthday? So we want to go to hours. Okay, so what we start with is your age. So on our next birthday, we're going to be 16 years old. So in 16 years, we're going to put that over 1. Now, yeah, if you're going to be 17, put 17 here. If you're going to be 18, you would put 18 here. And that's what we're going to do is use conversion factors to go down to hours instead of years. Okay, so if years is on top, years has to be on bottom. Let's do a conversion factor that goes from years to something smaller. Let's go to days. There's 365 days in 1 year. Oh, now my years can cancel out, so I draw a line through it. Okay. I've got days on top. I better have days on bottom. Let's go something smaller than days. Let's go, well, I guess we can go 1 day is equal to 24 hours. Okay. My days will cancel out. And so can I stop here? I've got hours, and it's asking me for hours, so yeah, I can stop. So now we can throw on the equal sign. 16 times 365 times 24. That number will go on top. 1 times 1 times 1, of course, is 1. And so let's do 16 times 365 times 24. And so I'm getting so this number, let's see, 140,160. And so divided by 1, of course, is itself. So 140,160. You can't just circle it again. You got to have the units. Please always include the units. We're talking about hours. So we'll put on hours and then circle it. Let's see if we got, well, I don't think I'll have an answer because everyone's will be different. But so if you were 16, if you're going to be 16 on your next birthday, that's how many hours you will have lived. Of course, it's going to be different if your number was 17. Yeah, it's going to be more. Or 18, it's going to be a little bit more than that. Okay, practice problem number 24. I think this is the last practice problem in the guided notes, so let's go through it. It says, how many pizzas do you need to order if 32 people will attend a party? Each person eats 3 slices of pizza, and each pizza has 8 slices. So, a lot going on here. Let's figure out, let's see if we can make this a little bit easier. So, we want to know how many pizzas. That's what we're going to circle. That's what we need to know. What we're starting with is 32 people. Okay. And then these other numbers here, each person eats 3 slices of pizza, and each pizza has 8 slices. These are conversion factors that we're going to use. So again, step 1, let's write down what they give us, put it over 1. So we've got 32 people. And I'm going to put that over 1. Okay. Now we're just going to convert using conversion factors here. If people's on top, we know that people has to be on bottom. Okay, is there a conversion factor that goes from people to something else? Well, yeah, it says each person eats 3 slices of pizza. So one person eats 3 slices. Okay, now my people divided by people is 1, so I can cancel that out. It's gone. Now I'm to slices, but I can't stop there because I want to know how many pizzas. So I need another conversion factor here, so I'm going to put in another one. Slices is on top. We know that slices has to be on bottom. And this last sentence, or this last part of the sentence here, gives us our conversion factor. Each pizza has 8 slices. So 8 slices is 1 pizza. Okay. And so my slices is going to cancel out, because slices divided by slices is 1. We can cancel it out. And I'm left with pizza. And that's how many I wanted to know. So we're going to take 32 times 3. Let's just do that one. 32 times 3. 96. I didn't do times 1 because anything times 1 is itself, of course. So 96. And 1 times 1 times 8 is 8. So 96 divided by 8 is equal to 12. Okay. But I can't just circle 12. It's 12 what? It's like, you got to tell people what you're talking about here. So 12. What's my units? We look to the last one that's still there, and it's going to be pizzas. Okay. 12 plural. 12 pizzas. Okay, so if you have 32 people coming to your party, each person's going to eat 3 slices of pizza. Each pizza has 8 slices. You better order 12 pizzas. So kind of cool. It's a way of going from one unit to another. Let's see if we got that right. Yeah, and we did. So great. Okay. That section right there is one of the harder ones for students to learn. So if you need to watch that again, please go back through the video. We're going to go through it in greater detail in class, but I think that gives you a good start into learning conversion factors. And so if you're at this point in the video, you have learned enough to do the, let's see, it's called the Conversion Factors Worksheet in the student workbook. So take a second, do some extra practice with this, and get that Conversion Factors Worksheet finished up in the book. And then start this last section. Okay, so we're going to finish up this chapter, this introductory chapter to chemistry, by talking about accuracy and precision. Accuracy refers to how close a measured value is to the accepted value. So it's like saying how correct you are. Precision, though, refers to how close a series of measurements are to one another. I always like to use this as an example. So a bullseye. So this guy, he hit the bullseye right in the center. So he is very accurate. I mean, he is really accurate. He hit the bullseye in the center. Let's look at the second example. This guy he shot 3 arrows. They were all pretty close to each other, but he wasn't at the bullseye. So we would say that this guy's precise because all 3 of his shots made a pretty tight grouping here. But he wasn't hitting the bullseye, so he's not accurate. So this would be an example of something that is precise but not accurate. In science, what would cause this? Maybe you're using equipment that just isn't calibrated, or something's wrong with your equipment that you're using. That can cause you to be precise but not accurate. Now let's go to this third example. This guy has shot 3 arrows and he hit the bullseye every time. So this guy's accurate and precise. His grouping is very tight, he's precise, and he's hitting the center. Okay, now this last example, he shot 3 arrows, but they were all different, in different places. So the grouping is huge, and this guy is not accurate, nor is he precise. And so this would be maybe your equipment's off, but also maybe your calculation, the way you're doing the problem is way off. And so you're not accurate nor precise. Of course, we want to strive to be like this third example here, where we are accurate and we're precise. Okay, representing data. We're going to talk about graphing for a second. A graph is a visual display of data that makes trends easier to see than in a table. So I've got an example here on the left. This is a data table. In science, we see data tables all the time. This is a data table. Okay, and they tell us good information. They really do. But if we can take the information from a data table and throw it into a graph, this makes it much more visual for people, and we can see the results much faster. I mean, obviously, you can just look around in this CF12 right here. 28% is the largest one. And we can get the same information in this data table, but in a graph, it's just more visual, and we need to learn how to read graphs. This right here is a pie graph, but there's a lot of different examples of graphs. A circle graph or a pie chart has wedges that actually represent percentages of a fixed whole. And so this would, 28% here, 23% here. It's all a percentage of made up of 100% if the whole circle is 100%. And so, yeah. Okay, bar graphs are also used a lot to show how a quantity varies across different categories. So we can have a single bar graph, a double bar graph. We'll explain more about those in class. Line graphs. In all graphing, there's a couple of variables that we'll talk about. An independent variable, which is independent, which means it's on its own, it doesn't change. And then there's a dependent variable, which is dependent. It means it changes. It depends on the independent variable, so it changes as a function of the independent variable. And so the dependent variable can change. Well, this is kind of important to remember with graphs. We'll go over it in class. We'll make sure we understand it. But the independent variable, the one that doesn't change, is always plotted on the x-axis. Okay. While the dependent variable, this variable that does change, is always plotted on the y-axis. So the y-axis is the one going up and down. The x-axis goes horizontal. So if we look at this, I like this second example, the B, a little bit better. It's graphing temperature as the elevation changes. So what is changing here is temperature. That's dependent. So that's going to be on your y-axis. So that's why you see temperature over here. It's changing as a function of the elevation. And obviously you can see as the elevation gets greater, so we climb elevation, what's happening to our temperature? It's going down. And you'll notice that as you climb a mountain, you're going to get, or in an airplane, as you climb altitude, the temperature is going to be decreased the higher you go. And so, anyway, that's graphing, and that's the chapter. So hopefully you've made it through. If you need to watch any part of the video again, it's very easy to scroll back through, watch those parts that you need to, and hope that helped. So thank you. Okay, you now know enough to complete your conversion factors worksheet in your student workbook. And these problems involve a lot of steps, so if you need to, go back through the video, watch it another time or two, and hopefully you can get them all done. Good luck.